So basically what happened, I can show you because I did put like the lectures here and then I'll kind of use support. But I don't want to, since we already lost some time, I don't want to kind of like write it down. Okay, so this was the issue that I had, like, and that's kind of what confused me. But let's see, I kind of like wrote, okay. So if you have, if you have two curves, right? Like there's a region between the curves, right? And like imagine that you start rotating that region with respect to the y-axis. That's how you get the solid of revolution. So what is the formula for that? So the formula I had written before is totally fine. There's like not an issue with that. But the idea is like, because you can kind of do it from first principles. So the idea is that you can say, okay, so, if you can still break this region into mini rectangles that have width dx, and the length of this rectangle would just be the difference in the functions, you see? So like kind of like, if you think about it, like this rectangle has like area height times width. And so that would be the area one of these strips, which when you start rotating gives you the cylindrical shell, right? Which I won't try to draw here because that's too confusing. But so this formula is completely correct, okay? So there was nothing wrong with that, like the way I wrote it, that was not a problem. But like the way it's set up, it's definitely had to be positive, right? It couldn't come out negative. That's how I realized last time that I made a mistake. By the way, like, it is kind of better if you detect that you made a mistake just to be like, oh, I know this is not the right answer. Because like with volume, it's very easy to figure out if you find like a negative number. So I prefer if you're saying like, oh, I know it should have been positive, but I made a mistake. It went negative. I'll probably reward that more than just like pretending that, oh, it's negative, but there's nothing wrong with that. So if you made a mistake, it's just better to, I would take less points if you're just upfront about it, because it's kind of like you're kind of realizing that you did something wrong. That's kind of why I realized last time that it was an issue, because I was like, okay, this is odd because it's coming out negative, right? So the problem I had, just to explain, like, which was very silly, is like, the problem is that I needed this integral. That was like the one that gave me issues. And if I was being lazy because in the first example or the second example, I had computed like the value for the integral. But let me see where I wrote it better. The thing that I forgot, the thing that I forgot in that example is that I wanted to put root of 5 minus 1 here, but the kind of like both the bounds and the function itself dependent on R, right? So let me put it like like it's better for me to explain it on the board, like this part on the board. So like in the example, what I had done, like I think in example 2, what I had computed had been like, yeah, something like this. And I needed So this is what I needed, and I wanted to use this example, but I was only paying attention, right? I was only paying attention to this number, right? So that's where I was taking this to be root of 5 minus 1, right? But if you put root of 5 minus 1 here, that messes up like the integrand, right? The issue that messed me up is like I was calling this R, so if you put root of 5 minus 1, you would have to get it here and here. And like that like no longer matches here because that should be 2 and 2. So the problem is that both the bounds and the integrand dependent on the value for R, and not just like like not just the bounds. And the other issue that I had was that I kept calling that like I should have called this like A or a different letter, because R is kind of like you can think of it as like as the radius, but like since we're talking about these problems of solids of revolution, then there's kind of like a radius, which is like the one that you use to revolve the region. So like, there was like a double meaning. So the point is that because of like the integrals being different, you could not compute the, like, this, like you had to compute it directly. You could not just like appeal to the previous formula. So this needed to be computed directly. It's not too bad to do. Like, it's like, again, I was kind of being lazy with that. So that's where like the issue came from. Like just like a misapplication of the formula, because I totally forgot that the function change also when you plug the value for r. Is that making sense? But it's still like it was good example in the sense like, that is how like, one of those things where you make a mistake and you're like, okay, what happened? Because you have to fix it. And it's kind of like, sometimes like in real time, it's more valuable to see like what the, like, when a mistake occurs and when everything comes out perfectly. But, so like the PDF has like full details about that, just FYI. So, but and it wasn't like too bad to do per se. It's, but I still, it still was an annoying thing. Um, but like the PDF has like all the details, as I was saying. But right, for now, that is more or less what I wanted to say about volumes, because I did want to move to a different topic today. Are there any questions about this? So because like the projector isn't working today, what I'll do is kind of like type the notes on the PDF, still send them to you. So you're trying to record it, but it won't look as nicely. Okay, so today what we want to talk about is like arc length. Maybe where do I have my color chalk? Okay, so what is the idea with the arc length? That is the length of a curve. That's basically what we're going to try to find. So length of a curve. Um, and to be more specific, we want to think of that curve like or being given by the graph of a function of one variable. So like the idea is that, think of like maybe this is a graph of a function y equals f of x. You take a value a and a value b, right? So each of these values gives you a point here. Okay. And then it's kind of like a piece of the function that is between these 2 points, right? Like so we want to find so think of it as kind of like as a piece of wire, or if you like, if this is kind of like a road on the plane, that would be kind of like if you're driving along this road, how much distance do you have to travel from going from this point to this point? That's kind of like the length along the curve, right? It's not like the distance, like in the sense of like a line segment, because that wouldn't be along the curve. So we want to find the length of this part of the curve. So that would be kind of like the distance you would travel. Um, is that making sense? Kind of like with the like so. Okay, and then you want to think how can I find this distance? And you want to do like, of course, like a calculus approach. So any calculus approach is to, again, whenever you want to do calculus, kind of like the idea is to break up the object into pieces that are more easily understood. So essentially what I'll do is kind of like a cute trick. I want to do it kind of more curvy so that I don't want to make it look so straight. Let's see. Okay, what gives? Let's not, yeah. Okay, so let's say you have the point A and the point B there. What I'm going to do is kind of like introduce intermediate points on the curve. Okay, and the idea is that I'm going to think of the curve, like, I'm going to connect these kind of like points using line segments. So, for example, this one gets connected like this. So what I'm trying to kind of like convey is that the line segments are not on the curve itself, right? They're relatively close to the curve, right? If you think that the points are, if you kind of like have chosen a lot of points, then these line segments are like, are a good approximation to the curve, right? Um, but the points but the line segments themselves are not on the curve. But the reason for doing that is that it is easy to understand find the length of a line segment, right? So let's just focus on one of these. So just to kind of like zoom in, I'll try to kind of like zoom in here. I'll call this H. You'll see why in a moment. But let's think of this as like, okay, you wanted to find the length of that line segment. Okay, so what I'll do is secretly draw kind of like a right triangle. So the H stands for hypotenuse because it's like the right triangle. Okay. So according to Pythagoras theorem, right? What is H? Well, Pythagoras, let me just try to see if like this is readable from the computer. So Pythagoras theorem says that H is the square root of delta x squared plus delta y squared. So I'll stop here to see if there are any questions so far, so good. Since okay, okay, so that is H, right? But what is delta y? So you have to think about this looks a bit better. If the points were really, really close to one another, this yellow segment would be more or less like the tangent line, to the curve. Okay, that's like, that's actually how the tangent line is defined. If you remember, like you kind of like look at the secant lines and then there's like a limit involved. So when delta x is really small, that's why I'm calling this delta x and delta y to remind you of the calculus notation. When delta x is really small, this is not that different from the tangent line. So delta y over delta x, right? That's kind of like rise over run. So that should be approximated by the slope of the tangent line. So what the idea is that roughly delta y over delta x is roughly y prime of x. Because it's like that's the slope, the tangent. Okay, so we're doing everything kind of like not super precise, so like just pretend that it's like an equality. It's in the limit is so perfect. So you just pretend that this is all equal. This is what you would call like the linear approximation before, for like the function. So you would say that delta y is y prime y prime of x is delta x, right? So why do I want to do that? Because then I'll plug that in back into the formula for the hypotenuse. Oh, let me put it here. So if you plug that back, and okay, so you have to square this. Square this like means like squaring each term. Okay. Okay. And then what can you notice here? That both factors have delta x squared inside the square root, right? So you can factor out the delta x squared, and then it comes out of the square root just as delta x. So you can kind of like, there's like some convenient factorization. Let me see if I can put it up at this end. Again, I'll write this on the iPad later, like I send it to you. But you don't have to worry about this. So if you factor out delta x squared, it will come out as delta x. Let's put that outside the square root. I'll put it with like kind of close the square root here. And so once you factor out delta x squared, this just gives you a 1. So you end up with 1 plus y prime of x squared. So that means like just to kind of like put like the steps together, that means that the hypotenuse is roughly, the length of the hypotenuse is roughly the square root of 1 plus y prime of x squared times delta x. Okay, so that, what does that correspond to? That corresponds to the length of one of these tiny hypotenuses, right? But then there's like another hypotenuse here. There's another hypotenuse here. There's another hypotenuse here. There's another hypotenuse here, right? There's another one here, right? So what is the total length, right? Like the total length should be approximated by the sum of all these lengths. So the length of the curve that we want, like I don't want to erase the picture, that's why I keep writing here. But the idea is like the length of the curve should be approximated by the sum of the lengths of these hypotenuses. Right? Well, the keyword there is sum, right? Because to make the approximation like legit, like you take an integral and then you're done, right? So like the actual length of the curve from A to B, so that's kind of like the formula of the length and there you go. But is that making sense up to this point? Uh, so again, the way you have to think about it is kind of like you know, you're adding up together the lengths of these line segments when you break up the curve into kind of like or approximate the curve into like line segments. Yeah.
So if we were just like doing the same thing, except we did everything with respect to the y-axis, then we just like switch it out for like. The limits along the y-axis and then.
Right. Yeah, like yeah, if somehow this could also be written as the graph of like, you know, what like x equals g of y or something like that, it kind of all works the same. You would just put what x prime with respect to y, like you know, like all the roles get reversed and you integrate with respect to y, etc., etc. But yeah, like the thing is like in practice it's very unlikely for the function. Like if you have like a curve, it is very hard to expect it to be simultaneously like kind of like the graph of a function of one variable in terms of x and in terms of y. So usually it would be one over the other. But I'm mostly interested in like, you know, the cases where it's just like as a function of x, because there's not really any conceptual difficulty, you know, when it's like a function of y, you just reach notations, like, you know, I will do like the cycloid, which is a bit more interesting example. And that does have like a slightly different feature, because it's not super easy to write either as a graph of x or y. And then that one is cool. But yeah, if it's just like a function of y, like you know, put like you kind of like put dy here and put like you know g prime of y here, etc. Like, and then everything is stays the same. If that makes sense. Um, Okay, let me start with a warm-up problem. By the way, I should say this is extremely hard to integrate. Like these integrals, you really have to be really, really lucky to be able to integrate them because it has like a square root. Integrating things with square roots is kind of like a pain. So like it is not like you have to kind of like choose like a very strategic example for it to give you something realistic to do. So there are not that many good problems like you can put here because it is like a really hard integral to do, like you know, in general. So this is like a hard is it hard to integrate because of like the square root? So just to give you for like, I'll give you like an example, like or like almost like a non-example because I won't integrate it, but just to give you how like a sense of how easy it is to not be able to do anything, like So like let's just take something. Okay, lines are fine. That's nothing to worry about. But let's take something like a parabola, which you could say, okay, like that's kind of like the after a line, that's kind of like the most easy thing you could think of, right? So like here's like a non, I'll call it like a non-example because I won't try to integrate it. But let's say y equals x squared, right? You have the parabola here. And I don't know, maybe you want the, like, it doesn't matter what you put. Maybe you want the length of the parabola from like x equals 1 to x equals 2, whatever. Like that won't matter too much. Okay, so what is so yeah, what would be the length of the parabola? According to this formula, it would be the integral of from 1 to 2 of the square root of 1 plus y prime of x squared dx, right? Oops, there it is. Well, but what is y prime here? Y prime here is 2x, right? Um, and so far so good. Does that make sense? And now what is that? Because I don't know. It's just like you know, okay, but so what? Like like I mean, of course, like in practice, like you don't care anymore about these things. These problems have disappeared because you just put it in Wolfram Alpha or a computer, and you get an approximation which is as good as you want to like the length, and that's all that you care about in practice. But if you were to actually be like, oh, give me the value for this, like a closed formula, right? Like not like an approximation that you can put it on the computer, then you're more or less stuck. Like it's not super easy to, like yes.
Would you use uses?
Like the thing is like, well, let's try it. Like let's just try it for a second. Like let's see. I don't think this one saves you. Let's let's say like, well, like I imagine by u sub you either want to do 1 plus 4x squared or 4x squared, right? Like I guess like those would be the natural. Okay, so let's go with that one. Yeah, like this is like a fun exercise to try. So you kind of like want to give this a shot. Then du is 8x dx, right? You see where it happens, right? Like you kind of like this x is missing, so you get stuck, right? Because like if we had, I mean, just to kind of like put it like more explicitly, you could say, right? I mean, yeah, like you could write this as root of u, but then dx is like du over 8x. So you have not really succeeded because you have to write everything in terms of u, right? And writing everything in terms of u does not like make your life easier. You can solve this for u. So it's u minus 1 over 4 root of. And I can promise you, you don't want to try to like integrate this thing. Like it is, like, it doesn't improve. Like it is. But I'm just saying, like already for a parabola, it's kind of like a mess. So my point is like the it is like a very elegant formula. But if you want to kind of like find actual closed formulas for the length, you're kind of like stuck for the majority of examples. They have to be very carefully chosen that you have like a miraculous integral that you know how to do. You know what I mean? Which is the one I'm about to do. I'm going to do like one of the miracle ones, like, because like this is like the point of this class where everything can be integrated. But like 99.9% of the functions that you would put there like will not have like a closed formula. Yes.
Sam, It's.
Yeah, or I would just be like, set up the integral, but do not integrate it. Like, I would be like, give me that formula, but don't try to integrate it. But I would say explicitly do not integrate it because like, yeah. But the thing is like, really, it is hard to find like a interesting example because there's almost nothing like I could write here that would give you like a nice formula. Yeah. Well, I think on the online problems, on the MyLab, on the the first one, I think they all should be able to integrate, or it would just explicitly set it up.
It won't be like.
Right.
Next in terms of you.
Yeah. No, like it wouldn't be like that. I mean, right, because I don't think the assignments have anything which is kind of like numerical, where like you can just give like an approximation. And I wouldn't anyways, like on the exam or like quiz or anything of that sort. But I just want kind of like to convey that this is like a nice form, like this kind of sometimes this difference between like, okay, you have the formula versus can you really use it? You can use it like if you just care about approximating, because that's for like Wolfram Alpha, it's for computers like ChatGPT or like DeepSeek or whatever, like all these things are for. But like, not really if you want to have like a very nice, elegant expression. So let me give you one of the few examples where you can do this. I'll give you two. Okay, but at least now we understand that this can be like a painful thing to try. So here's one. Here's like an actual example. Like something like x, say 1 plus x to the 3 halves. For like, I don't know. Well, if I do it that way, I'll do it. Okay, so what was that graph like? Because I remember it. I mean, it's kind of like what is that? It's some sort of like square root, but it also has like a cubic inside of it. So I mean, it have like it's like the graph qualitatively it will be a combination of those. Not that you need to kind of like, I'll just show you the graph. Um, sorry. Kind of like no, the graph like doing this problem because like you just like the integral, but let me. You know how much I can use the other here, but it's so right. Like the function I had what y equals 1 plus sorry x to the 3 halves. Okay. Yeah. So like it's even how the way it looks is like qualitatively, if I just show you that, like you would think, oh, maybe that's like a parabola. It's not so hard, not so easy to distinguish it. But uh, but yeah, we just want the length of it between what 1 and 2. So we just want this tiny bit segment that you see here. Yeah, we don't want the entire graph. We don't want the length of the entire curve, like for the graph. We just want this piece. Like, how long is that? And I'll show you like why this one works nicely. Okay. So for all these problems, you need the derivative. Derivative of a constant is 0. So the 3, this comes like brings down the power, the exponent, and increases by 1. Right. So 3 halves minus 1, that is 1/2. And that is where like that like things will become easy, because then you also need y prime squared, right? So y prime squared is 9 divided by 4. Well, the 1/2, well, there's like a square root, so you just get x, right? And this is easy to integrate because there like a regular use of does work. So what would be the length? The length, because x is going from 1 to 2, with the integral from 1 to 2 of root of 1 plus 5 prime squared, so 1 plus 9/4 times x dx. So what makes this easier is that it's in linear in x inside the square root. So it's kind of like just like a regular change of variables, or like a use of that will work. So, if you want to kind of like rewrite this a little bit better, is it one? I mean, if you just want to play first with the, like, use a common denominator and then pull out the like take out the 1/4 as a 1/2, and it looks like this a bit better maybe. But it doesn't matter. That's more cosmetic. Like you just make u the inside of like the square root. Like that's all that you really cared about. So if you do u equals 4 plus 9x, right? Then du is what, 9 dx. No, not too bad. Sorry, I should have put here dx. My mistake. And du over 9 is dx. Right, and then well, maybe I should erase that, but I'll write it later. So, when you do like these use stops, like there are two options. Either you change the bounds with the use stop, or you leave the bounds intact, but then you do like the antiderivative first, and then like I'll just change the bounds with the use stop because like that's also useful to know how to do, right? So when x equals 1, what is the corresponding value for u? So it would be 4 plus 9. 4 plus 9 is 13. So I'll put here u equals 13. When x equals 2, what is the corresponding value for u? It would be 4 plus 18, which is 22. And then this just becomes root of u. And the dx is du over 9. So that's perfect. Right, and in fact, just to make it easier to remind us how I'm going to integrate this, like root of u can be written as u to the 1/2. Right, and then you're more or less good to go because it will be 1 over 18. And then what? You add 1 to the exponent, so it becomes u to the 3/2. And then you divide by that number. So you divide by 3/2. And well, this has to be evaluated at the bounds. Okay. So what? Like it will give you like the 3. Well, it's like a 2/3, right? Like so, it becomes 2 over. And that is 1 over 27. I mean, whatever, like, I could have chosen like better numbers for this, but it's just kind of I wouldn't expect you to simplify before beyond this point, because like there's no nice numbers for like, what that is. And that means more. Oh, sorry. So the things like there was like a 4 here, so I made like a common denominator, right? So that makes the denominator here a 4, and I took it out of the square root and it came out as a 2. Yeah. Sorry, but yeah, good point. Okay, but literally, short of something like this, it is hard to find something where you can explicitly, just like come out and integrate every single step. Now, there is like a very nice curve called the cycloid. So let me tell you about that one because that's also one of the other few ones where like you can actually integrate things. And And it's one of like the more famous curves in like mathematics, so it's kind of like nice to talk about. Okay, so let's talk about this one. So what is the cycling going to be? I like this animation a lot. And then I'll show you another one. Okay, so imagine you are on a bicycle and we're going to keep track of a point on the one of the wheels of the bicycle. Okay, so just imagine like you put like maybe like you like you put like a post-it note or something like something that will you know something that will like like single out this point. And you want to keep track of it as you like, you bike. So that what the curve, if the curve that this point makes on the plane is what we call like a cycloid. Okay, so that is a cycloid. It just kind of like appear in many different places. So for example, imagine you turn it upside down, right? Um, if you turn it upside down, it kind of, and imagine you have like 2 points here and you have like a chain that's hanging from these 2 points. The shape under like uniform like under gravity that it gives you is like a cycloid, which is kind of like called the catenary in that case. Like this. Actually, I'll give you like a problem about that like next time, but like it is like a cycloid as well. Um, and it also appears in other things, but it is one of like in fact like it has like a again like some fun history because Galileo originally thought it like kind of like for like a problem like he had been given this problem like what should the shape be? He thought it was a parabola, and then then Huygens or like one of these people like later like solved that it had to be this like shape. This is actually related to something that's called like a hyperbolic cosine, which I'll tell you about on the workshop for this week. So like it's kind of like a cute thing, but it does appear like everywhere. So anyways, like what I'm bringing this up is because this is one of the few ones where like one of the few curves where you can actually find its length. So that's kind of what makes it nice to kind of like think about it for a second. So just to go to a different like you know to a different animation. Let's see. So the thing with the curve for the cycloid, it is that it is hard to kind of like give like if you just of course like you just imagine focusing on this first part of the curve like once you start to like if you think of the point starting at the origin, it has like the circle has like a certain radius that's like the circle like the radius of the wheel. So just imagine this part, right? It can be hard to give like a explicit formula for like y in terms of x for that thing for this part of the curve. It is easier to express like the position like the x and y coordinates as a function of time. So just like imagine keeping track of the x coordinate and the y coordinate, that is how that changes in terms of time. And so you get this, and I'll kind of like find the curve, like the length of the curve using this. So imagine like in principle, you could solve like write y as a function of x, but that's kind of like messy. What I'll do is kind of write y and x in terms of t, in terms of time, and that is kind of like simple. And I can use the same formula with the chain rule trick to find the length. That's kind of like the cool thing. So Okay, so. So just again, like, just to say a few things about the cycloid. It's just kind of like the curve generated by a point. On the wheel of a bicycle. That's one way to think about it. And let's say the bicycle has radius r, like the wheel, I mean. And it kind of looks like this, but it is easier, easier if x and y in terms of t instead of so this is kind of like one of these like implicit differentiation type problems for finding derivatives. If you remember from Cup one, like um, instead of y as a function of x. So like the formula that I'll go with is just like the one that you saw in GeoGebra on the that animation. Just um, well, I have it on my notes. Sorry, let me check how I wrote it. Ah, here it is. Okay, so the idea would be to use the chain rule. And there's this trick formula that, yeah, I wouldn't expect you to not remember because, like, I myself wouldn't remember it, honestly, which is like this kind of like, so again, like by the end of the week, I'll kind of will give you like a list of identities that I could want you to know by hand, like, for the exam. But this is not one of those because I wouldn't expect you to memorize this one. It's a bit too complicated. To find the length of the curve, to by r, let's say. Oh, multiplied it by pi. Doesn't matter. Oh, yes, sir. Well, right, it's kind of like up to you how you want to set it up, but I'm thinking of the radius as being genuinely R, just R. But the thing is like kind of like here's what I'm thinking, if what happens if like sorry, like just to explain what I'm trying to do. Where should I put this? Okay, so what happens if you let me make it like a table. What happens if I plug in t equals 0 in these two formulas? So this gives you 0 and sine of 0 is 0, right? So 0 times whatever like gives you 0, right? So that gives you 0 here, right? And then cosine of 0 is 1, right? So 1 minus 1 is 0, so you get y equals 0, right? So t equals 0 corresponds to precisely this point. Yeah. Yeah, that's kind of actually was going to say later, but like, yeah, it's good that you asked me now. And then what happens if I can place p equals to 2 pi, which is kind of what I was looking into. So if I put t equals 2 pi, so I get 2 pi. Oh, sorry, the 2 pi comes from like, yeah, like from the time, like the angle, because I'm thinking of t as the angle also. So yeah, I don't need a pi, but thanks, like actually, like this fixed it for me. Yeah. Because if I put 2 pi here, like, yeah, then this gives you 2 pi, right? And sine of 2 pi is 0, right? So you get just 2 pi r. Okay. And then here, what is y? Y would be 1 minus cosine of 2 pi, but what is cosine of 2 pi? That's also 1, so 1 minus 1 is 0. So what I'm saying is that after 2 pi times 2 pi, right, like assuming some units or whatever, you're here. So this is kind of like the length after a complete revolution on the bicycle, right? Because like if the circle is radius r, like the length of the circumference is 2 pi r. So this is kind of like when like you have done like a full revolution, like the bike, like the wheel has done like a full revolution. That's like when you have like moved 2 pi r in terms of like length. So this corresponds to a value of x equal to 0 and x equals 2 pi r. It will be the last example I do today, by the way. Because like we had like this malfunctioning of the projector. So I'll kind of like call them so that they have it fixed before next class. But is that making more sense now? So yeah, I should have hood. Right, like that's what I wanted to, like that's what I meant for these bounds. Okay, so how is this related to like to implicit differentiation? I don't want to again, this was the formula for the integral in general, right? But now what is y prime of x? Like this is where you have to be like, think a bit more of what's going on here. So what is y prime of x? That is dy dx, right? In general. But by the chain rule, if you think everything is depending in terms of t, it's kind of like, that's kind of like the cool thing about writing the derivative in this way, because it's almost like a multiplication and division kind of thing. So it is the same as dy dt times dt over dx. Okay. Or yeah, like that's fine. That's one way to write it. And then, this is the same as dy over dt divided by dx over dt. Again, if you think about this as fractions, it kind of like works correctly, because but like the thing is like each of these can be found like kind of like easily from like the formula. So that's kind of why I wanted to do this example, because it's like a good reminder of that basically. Because dt over dx is 1 over dx over dt. But in this example, what is the y, what is the derivative of y with respect to t? Okay, so let's just work it out, set each of them first. So y was r times 1 minus cosine of t, which is the same as r minus r cosine of t. Okay, so dy dt is, well, like this is like a constant, so you don't see that, and derivative of cosine is negative sign that cancels that minus. I think it's just r sine of t. Okay, and what about the other one? What is the x dt? So x was r times t minus. Okay, and the x dt, if you, I mean, this is like a constant, so you just take the derivative of the inside and you get 1 minus cosine of t. Oh, well, I already erased that actually, but I'll kind of remind you there in a moment what that was. So y prime of x would be dy dt, but dy dt is r sine of t. Divided by r times 1 minus cosine of t. Okay, and the r's cancel, so that's sine of t over 1 minus cosine. I mean, it looks weird, but like, like it's what you get if you rewrite it, you can rewrite everything in terms of t because of like implicit differentiation. Okay, now, okay, so that fixes this part, check mark, 1, nothing needed here. Dx, I do need dx, but dx is kind of like hidden in this step. What is dx in terms of dt? What is dx? Well, we know that dx dt, right, is r times 1 minus cosine of t. So it's kind of like a use up kind of thing, right? Dx is just r times 1 minus cosine of t. Okay, and that allows you basically to rewrite the entire integral in terms of. And the idea is like doing the integral in terms of t is a lot easier than in terms of like x. So you have to play with the chain rule and all this stuff to kind of come out nicely. Yeah, sorry. Uh, oh, it will appear like in 2 minutes, like once you have to do the integral. Yeah, but it will be needed for the integral. Yeah. Yeah, because like here you don't need it at all. It's only once you want to actually do the integral. So, but good question. And what else? Okay, so and it will be the last thing that I'll do. So let's see. Let me just write the integral down. So the length becomes the integral of the root of 1 plus y prime of x squared. But what is y prime of x squared? It is sine of t over 1 minus cosine of t squared. Okay, and what is the x? The x is r times 1 minus cosine of t dt. Okay, and because this is like an integral for t, that's why I had to figure out the t bounds before. Like I wanted this to go from 0 to 2 pi. So. And this looks intimidating, but it's actually not as bad once you start simplifying it a little bit. Because what does that give you? It gives you like the integral from 0 to 2 pi. Yeah. 1 plus sine square of t, 1 minus cosine of t squared. Minus, 1 minus cosine of t. I'm sorry, this looks a bit bad. Maybe. No, it looks a little bit better. And then like again, like you really have to add these together. So like I'll do like a common denominator. At the BR, you can take it out of the integral. Again, we write this all like on the tablet, but like the R, like, like doesn't matter. Okay. So hopefully this kind of like taking shape, because this denominator, when it comes out like from the square, like this will cancel with this. Okay. Because this one is with a square inside the square root, right? So you just end like, so like now the integral doesn't look as bad. Okay, now you're like, how do you integrate this? You do have to expand this out. So I need to use like that, I still have that a minus b squared is a squared minus 2ab plus b squared. Okay, I will use it here. So you get 1 minus 2 cosine of t plus cosine square of t plus sine square of t. Okay. Oh, sorry, yeah.
It's fine.
Like this y prime of x to me.
Yeah,
The idea was like that, what is, sorry, just to kind of repeat it. What is y prime of x? That's dy dx, right? Right? But because of the chain rule, this is kind of thing. And here, like, you kind of think of it as literally being more or less like fractions. Yeah. Correct. Correct. Yeah. Yes. Yeah. No, it's like a clever trick, but it can be confusing. Like, yeah, like the first time you see it, and then I do expect you to not remember that cosine squared plus sine squared is 1. Yes. Oh, the thing is, like, it came out like before canceling. I have to take it out of the square root, and that's yeah. Well, but yes, like, it can. Let me just kind of like close off the square root so that it's clear that it's not inside. Yeah. Otherwise, we would be, yeah, and then this would not have been mentioned in this class. So, but it is really hard to get these integrals to come out nicely. That's kind of my point. And then like cosine squared plus sine squared equals 1. 1 plus 1 equals 2. That's fine, right? And then I can take out like a square root of 2. And I believe we're now getting close to the point of that identity that I wrote at the beginning of the problem, which like I deleted accidentally, because like the identity was for this, what was it, that like sine of t over 2 is like the root of 1 minus cosine of t over 2. Is that what I wrote before? Is that like a 2 there? Yeah, I guess that's like the thing I don't remember. Of course, I would never expect you to remember this. Like, who would I would just kidding. But so, oh, perfect. So if you kind of like multiply both sides by root of 2, right? Sorry, I'm almost done. Like 2 more minutes. And then, perfect. I'll put that into the in the integrand. So that becomes root of 2 sine of t over 2. And okay, it is way easier to integrate, right? Like we know how to integrate a sine. So you get 2 r. I mean, you have to do like a mini u sub. That's not too bad, because like you just make u equals t over 2 to 1. So that will give you what? I think it gives you minus, let me check. right? Because cosine, negative sign, and then, yeah, it gives you that, and then. Okay, that thing is like with the bounce, like, because, okay, this is kind of, I mean, I should, the problem here, like, I mean, this is, like, it's almost, I should have done it like from 0 to pi or something like that, and which gives you half of the curve. Like, sorry, just to, I'll explain what happened, like, in a moment, but let's just change it to 0 to pi. And then if you do this from 0 to pi, then this just give you -4r, like -1. Oh no, because it is, oh no, like this is fine because it's pi over 2, perfect, 2 pi, oh, sorry. It's like, otherwise, like, don't, it's not needed, like. Sorry, because like this is like 2 pi over 2, so that is cosine of pi, so it's fine. The thing is like, okay, yeah, so that gives you -1 minus 1, so it's -2. That's -4r times -2, which is 8r. Okay, so what happened is like strictly what I was just to wrap this up, but like the idea is like, when you take out something from a square root, like you do have to be careful because it comes out as an absolute value, like, so like here the cancellation could have been plus or -1, but it kind of like comes out like to work in exactly the same way. So it does like it's not much of an issue. Like what this says is that, but kind of like the cute thing that this says is that when the wheel has like made like a full revolution, like the point of the wheel has traveled like, I mean, I think maybe could I be missing like 8 times like the radius, and I don't know if here's again, have to check if there's like a pi missing inside word, but I think it's fine. No, like it's, I can think, I would check that. I don't think there's any pies that I'm missing, so like that should be fine. But there could be because like of the units, but like the integral is correct. But I do think like drawing, but it doesn't weird here. Like, yeah, like I would have to double check the pi thing. But like the important thing is kind of like the trick of like the, chain rule and the bounds, like, and all that stuff. But it's like a sophisticated integral. I did want to do like, okay, this is too hard to have like an example, but like I did want to do like an example to show you, that these problems can get difficult like quite quickly, and unless you have like a very specific curve, like you kind of are stuck and don't know what to do. But like it's kind of more like the one with x to the 3/2, like the one that you should know how to expect. Okay, let's finish here, and then next time I'll tell you quickly about how to find like a surface area and like an area of surface of revolution, and talk about integration by parts, which is kind of like the important stuff. I'll kind of come here to see if I can fix this.